This is the second in a series of informal film reports on some of the test work at the Arnold Engineering Development Center near Tullahoma, Tennessee. Tests supporting Project Able-1, the Lunar probe, have been made in the high-altitude engine test cells of the Arnold Engineering Development Center. Approximately 30 solid propellant rocket motors of several different types and sizes were tested in the initial phase tests. The work thus far has been concerned with motors used for third-stage boost, for spin stabilization, for verniers, and for the retro rocket, which decelerates the probe as it approaches the Moon's gravitational field. The rocket motors installed in the third stage and probe section of the Project Able vehicle were tested under high-altitude conditions for various reasons. The 50-pound thrust spin rockets which stabilize the vehicle after second stage separation, and which also are used as verniers for final trajectory adjustments, were tested to check the effects of their exhaust on the third stage motor and the probe. The effects were negligible. The 900-pound thrust retro rockets were tested to determine total impulse and temperature distribution on their casings, for excessive heat could damage the instrument payload. Results were acceptable. However, the most significant test results were obtained during testing of the 3,000-pound thrust third stage motors. More than 20, including 5 different types, were tested. This is a calibration model of one of the third stage motors being mounted on a thrust stand before being installed in a test cell. Various types of nozzles were tested during the program. The tests were run in the high-altitude test cells of the engine test facility. Instruments recorded thrust, total impulse, the rate at which fuel weight decreased, and other aspects of operation. The objective was to compute precisely the gain in velocity imparted to the lunar probe by the motor. This is extremely critical, for even minute errors could cause the probe to miss its target in space. High-altitude conditions were created by pumping down the cell and its exhaust ducting to simulate an altitude of approximately 70,000 to 80,000 feet. For even higher altitudes, a tandem diffuser ejector was used. The rocket's exhaust is captured by a diffuser duct to produce desired pressure recovery, and an auxiliary ejector driven by air or steam augments pump down prior to firing the rocket. Altitudes of more than 100,000 feet were attained. This is a downstream view into the diffuser ejector. The particles in the rocket exhaust are grains of ignited solid propellant. This typical plot for one type motor shows the build-up to the 3,000-pound thrust level, and the drop-off as the motor nears cutoff at about 40 seconds. This plot indicates thrust versus time for another motor. All 6 of the motors of this type tested had a continuation of burning after the prescribed cutoff. There had been no indication of this in prior tests. The blips showed that the burst of burning, or chuffing, lasted almost 160 seconds beyond regular cutoff. Each represents an additional burst of 300 to 500 pounds of thrust. This test run shows the chuffing. As the motor nears cutoff, the shock diamond moves back into the glowing nozzle. Burning stops. Then, a few seconds later, some residual fuel reignites. The flame bursts forth, and additional thrust, or a chuff, results. This chuffing could cause the third stage motor to accelerate shortly after being separated from the probe and collide with it, probably bumping it from its prescribed trajectory. This type motor was disqualified for use in the Project Able-1 vehicle. A second significant finding was the failure of the nozzles. Various types of plastic or steel-reinforced plastic nozzles deteriorated when subjected to high-altitude operating conditions. These are nozzles prior to a test, and this film shows a nozzle failure. In some cases, the nozzle separated from the motor. Test data helped the manufacturer devise improved nozzles. This is a typical nozzle deterioration following high-altitude tests. The nozzles had operated satisfactorily when fired at sea level. The value of the test data produced during this program is indicated by the increasing demand for testing other and more powerful rocket motors, both solid propellant and liquid fuel types, at the Arnold Engineering Development Center. One of the most unique test programs ever undertaken at the center involved an actual flight model missile full scale of the turbojet-powered McDonnell Quail, which is a decoy missile air-launched from B-52 or B-47 aircraft. The missile was delivered to AEDC and testing began in September 1958. The test was conducted in the transonic circuit of the propulsion wind tunnel. Since the actual missile was tested, the structural integrity of the airframe could be checked at the same time that the engine performance was being evaluated. The Quail's General Electric YJ-85-3 engine was operated at full military power, and techniques were developed to successfully start the engine throughout the missile's mission envelope. Blowout and stall limits were determined, and the starting envelope documented throughout the missile's operational range. Mach numbers 0.75 to 0.95, altitude 35,000 to 50,000 feet. Before being installed in the tunnel, the J-85 was run up, and the engine's ethylene oxide ignition system for high-altitude starting was checked. Since the wind tunnel tests were conducted concurrently with flight tests at the Air Force Missile Flight Center, the tunnel data were transmitted on almost a daily basis to both McDonnell and Holloman. During the preliminary run-ups, a minor mechanical failure in the fuel system resulted in an accidental fire. Damage was limited to some scorched paint, and the incident helped spot a weak point. Had this failure occurred in flight, a missile might have been lost and the cause gone undetected. The missile was next installed in one of the tunnel's removable test sections and moved from the model installation building to the wind tunnel. It was fitted with strain gauges and other instrumentation to measure the dynamic loads. It was determined that the GAM-72 was flutter-free throughout its operational range. As a result of these data, the dynamic testing phase was eliminated from Holloman's flight test program, a substantial saving in time and money. During the test runs, with specific altitude and airflow passing through the test section, the engine was started and operated while being pitched at various angles of attack, from +15 to -5 degrees. Note the scavenging scoop in the background. It follows the nozzle of the engine to collect exhaust products of the burning engine and remove them from the tunnel circuit. Since the YJ-85-3 was limited to 15 hours of operation, 3 changes were made during the 15-day test. Operating time at full military power substantially exceeded the total log prior to wind tunnel testing. All major objectives of the test program were accomplished, and the wind tunnel data was acknowledged as an important factor in supporting the flight test program of the decoy missile. Critical propulsion and aerodynamic problems encountered in the development of the Atlas and Titan intercontinental ballistic missiles are being solved with the help of test data produced in the 3 major laboratories of the Arnold Engineering Development Center. Although ballistic missiles are outside the denser regions of the atmosphere and without power for most of their flight, they must pass through the lower atmosphere during launch and re-entry. It is in these critical areas that AEDC's work supports their development. One major problem is recirculation of explosive exhaust gases into the missile's base. Typical of AEDC's work in the engine test facility are tests made with this 1/20th scale model of an Atlas 3-nozzle base. Air is pumped through the nozzles at various Mach numbers and altitude conditions, and smoke or particles are released to trace the recirculation of fuel-rich gases from the turbine exhaust back inside the missile skirt. Fluorescent vapor shows the recirculation. Note the flow up inside the plastic skirt. Object of these tests is to provide data on which to base redesign of the missile base to provide optimum mission capability, yet prevent the risk of explosive gases within the base. Earlier tests were made using a 1/20th scale model of the two-nozzle Atlas base configuration. This is the test rig. The smoke probe can be extended or retracted. Note the backflow of the tracer smoke, and then, as the probe is extended, the smoke flows downstream. More recent tests involve this 1/10th scale model of the Atlas base for investigating recirculation of hot gases in the missile base. This model is being tested in the engine test facility. It has 2, and later will have 3, 1,000-pound thrust liquid fuel rocket motors. This is a run at a simulated altitude of 80,000 feet. Recirculation was detected by pressure and temperature measurements, gas tracers, and motion pictures. Supersonic phases of base recirculation have also been conducted in Tunnel A of the Gas Dynamics facility. In these tests, the 1/30th scale model was placed in the high-velocity airflow to simulate flight conditions. Tests have been made at Mach 2, 3, 4, and 5, at flight trajectory pressure altitudes of from 47,000 to 130,000 feet, and at angles of attack from 0 and 10 degrees. Various configurations of turbine exhaust ducts and the effect of base recirculation and base flow characteristics are being investigated in these tests. Similar testing on the Titan missile began in the propulsion wind tunnel early in January. Another test supporting the ICBM was the investigation of jet spreading and flame impingement of these vernier engines. A full-scale vernier rocket motor was tested in an engine test facility test cell. Notice the gradual expansion of the jet as this rocket is fired at pressure altitudes that are increased to simulate flight from sea level to approximately 75,000 feet. The heat flux into the missile body was measured and various flame deflector plates evaluated. Some tests have been made at approximately 100,000 foot conditions. Extensive AEDC work is being done in the aerodynamic areas in support of the ICBM program. One task is to help evolve nose cones with optimum re-entry characteristics. An earlier film reported nose cone tests in the hypervelocity area, Mach 10 to 20 and above, in the gas dynamics facility's arc-driven hotshot wind tunnels. However, equally important work is being done in the transonic and supersonic areas. This is a large-scale model of the Titan nose and boom under test in the propulsion wind tunnel. Object was to determine probe position error for angle of attack and Mach numbers. A series of static and dynamic stability investigations have been made on the nose cones of the Atlas, Titan, Jupiter, and Polaris. This is one of GE's RVX nose cones for nose cone research vehicle. It was tested to check the effect of Mach numbers, angles of attack, and various flight conditions on its stability, and thus accuracy. To evolve the optimum stability, accuracy, and impact Mach number, extensive measurements must be made. These probes record pressures in the wake of the missile. A small model previously tested in a 1-foot AEDC wind tunnel was mounted on the sidewall of the test section. Data produced in the smaller tunnel was thus cross-checked with that from the large test section. AEDC is carrying on its own re-entry shape investigation. Various combinations of nose shapes, center body lengths, and flared tails are being tested at transonic, supersonic, hypersonic, and hypervelocity flight conditions. This is one of the models in the 1-foot transonic test section. And this is the largest model of the AEDC shape in the 16-foot transonic test section. Objective of this program is to determine basic design information. Particular emphasis is being placed on data for advanced ICBM nose cones and other shapes which may be applicable to manned re-entry vehicles. In the supersonic area, the Gas Dynamics Facility's 1-foot tunnel has tested a small-scale model of the GE RVX model. Similar to the large model tested in the 16-foot tunnel, the smaller model was tested in a 1-foot tunnel at Mach 5. And this is the Schlieren film recording Mach 5 airflow. Test work aimed at providing the nation with the most accurate and reliable ICBM weapon systems possible. The value of a large wind tunnel for making critical aerodynamic measurements on a full-scale, actually flight-type airframe was demonstrated at the AEDC during tests on the Sergeant missile. This is the Army Ordnance missile in the 16-foot transonic section. The 4 drag brakes are used to regulate the range of the missile, normally about 200 nautical miles. Purpose of the test was to isolate the exact source of high vibrational loads in the missile's guidance compartment that occurred when the brakes were opened in flight. Tests were made at conditions simulating Mach 1.2 and 1.5 at 30,000 feet. One of the instruments used, this turbulence gauge, a small, highly directional microphone. These mics sensed amplitude and location of the noise caused by vibration and recorded this on magnetic tape. A typical noise signal sounded like this. Various shapes of drag brakes were tried, with various size openings in the blades. Mechanical adjustment and operation of the brakes were carefully checked prior to the test runs. It was suspected that some of the vibrational loads were being transmitted to the guidance compartment mechanically through brake linkage. To check this, special supports held the drag brakes in and extended position, but not connected with the missile. It was found that about 25% of the vibration was transmitted mechanically. A coat of fluorescent oil on the surface of the guidance compartment showed patterns of aerodynamic turbulence caused by the brakes. This first pattern was caused by blunt-shaped solid blades. Less turbulence is evident in the second pattern made by T-shaped blades. The test determined that the vibrational loads were caused principally by aerodynamic buffeting and flow separation ahead of the brakes. The program resulted in considerable saving, for flight tests would have required firing a number of specially instrumented missiles. Flutter investigations of the advanced Boeing Beaumark have been made in the 16-foot transonic wind tunnel to determine the proper stiffness of wing and tail surfaces. In the first part of the program, a semi-span model with a single wing aileron attached to the body was shake tested. The wing was vibrated mechanically to find its natural vibration node point. An accelerometer was used to detect vibrational frequencies and establish the node point, the axis of no vibration. The aileron was then connected with a solidly supported wing by a linkage that provided for various stiffness ratios. The surface was then shake tested at various frequencies of vibration to determine the natural frequency of the surface. The frequency of the vibration at various stiffness ratios was basic knowledge required before the test could be made. These high-speed motion picture films show flutter with surfaces of relatively low stiffness. This first is a view of the wing aileron flutter characteristics at approximately Mach 1.2 and at an altitude of 30,000 feet. In this run, the surfaces have relatively high stiffness, as model was subjected to Mach 1.5 airflow at a simulated sea level altitude. This is a non-flutter condition. The program defined flutter conditions for a wide range of structural stiffnesses of the wing and tail surfaces. This permitted Boeing's engineers to make a compromise between stiffness and weight, and to establish the stiffness ratios required for compatible matching of wing and tail surfaces so that the advanced Beaumark mission may be accomplished. The foregoing are only a few of the many programs recently completed or now in progress at the AEDC. With more than 20 test units in operation, there are many additional aerodynamic and propulsion tests. Typical of transonic aerodynamic work in the propulsion wind tunnel was a test of the Northrop T-38. Drag, stability, and flutter were investigated. Other transonic tests investigated the Convair WS-125A's configuration, and drag tests were aimed at increasing the range potential and cruise speed of the Northrop Snark. Flutter tests of the F-108 wing and ailerons indicated an ample margin between flutter boundary and operating range of the aircraft. This is the ventral fin, failing at a point well beyond the operating range. The Gas Dynamics Facility has done extensive work in the category of supersonic, hypersonic, and hypervelocity aerodynamic tests. This is a Tunnel A test of advanced configurations of the Convair Super Hustler. These were in the Mach 2 to 5 areas. Data helped develop better inlets and a reduction in drag. In the facility's E1 tunnel, a variety of shapes from the Wright Air Development Center were tested for stability and drag data in the Mach 2 to 5 range. The hypersonic test work included prediction of aerothermodynamic loads and heat transfer measurements of the North American X-15 research aircraft at Mach 7 in Tunnel B2, and similar tests at Mach 8 on the Navy's IRBM Polaris. AEDC is also carrying on extensive tests supporting the Dinosaur program. These are some of the Martin Bell shapes as they are prepared for test and installed in one of the arc-driven hotshot tunnels at the Gas Dynamics Facility. And these two runs show Boeing shapes subjected to velocities of Mach 17. Stagnation temperatures in these runs were approximately 10,000 degrees Fahrenheit. Tests for both Boeing and Martin Bell are underway in transonic, supersonic, hypersonic, and hypervelocity areas. A number of test programs have also been active in the propulsion field. Work is being done in the engine test facility for General Electric, Marquardt, and Pratt & Whitney. One turbojet development program of interest involved the Pratt & Whitney J75 engine, fitted with the inlet ducting representing installation in the Convair F-106. Object of the test was to investigate the effect of cooling inlet air with water sprays to extend the Mach 2 limitation for the engine. The chart shows the J75's operating envelope and how various increments of the water-air ratio used for cooling the inlet air extended the afterburner blowout limit and the Mach number limit. This Mach 2 engine was successfully operated at conditions simulating flight at Mach 3 and 82,000 feet. This principle might well provide for a tactically important high Mach number and extreme altitude operation for brief periods of time. The Canadian Orenda Iroquois is also being tested at AEDC. The program involves several different versions of the engine and includes investigation of the internal aerodynamics, testing of the afterburner, and controls evaluation. Another unique test investigated the feasibility of recovering the RVX ballistic nose cone by means of a parachute in order that ablation, or the effect of heating, during re-entry could be determined. The nose cone was cable suspended in the 16-foot transonic wind tunnel, and various types of parachutes were deployed from a recovery package in the base of the missile. 2 actual flight attempts at recovery had been failures. When the first parachute tried was deployed at approximately Mach 1.5 and at a simulated altitude of 33,000 feet, the parachute failed to fully inflate due to the turbulent weight behind the nose cone, and a violent squidding action resulted. The 3-day test included 16 shots covering the Mach numbers from Mach 0.85 to about 1.5, and altitudes between 21,000 feet and 33,000 feet. This shows a successful opening which was accomplished when length of the chute's shroud lines was extended 50%, from 8 to 12 feet. Cook Research, manufacturers of the recovery package, were able to fit the revised chute and its longer shroud lines into the original recovery package when drag measurements, lower than expected, indicated that lighter material could be used for the shroud lines. Thus, the center of gravity of the nose cone was maintained, and no major redesign of the nose cone was necessary. This fix was proven successful in a flight test following the wind tunnel test. 16 shots were made in the 3-day program. Determining this information in actual flight would have been much more expensive and time-consuming. The work of the Arnold Engineering Development Center, part of the Air Research and Development Command, is thus covering a wide spectrum of testing important in supporting almost all of the high-priority weapon systems of the nation. Subsequent film reports will describe more of this work.